Hello everyone, welcome to the optimization video. So here is where we solve maximum minimum problems, also known as optimization. So the first thing we're going to discuss are the steps that are generally involved in an optimization problem, and then we will jump right into our first example. So I will start this off with a little bit of a kind of a cautionary, something before we start going through the steps, something to keep in mind. For most people, the most difficult part is the first two steps, and these are where you are responsible for coming up with the equations yourself. You design the equations to be maximized, minimized, and you do so using what's called a constraint or a restriction, if needed. Okay, it's not always needed. This tends to be, like I said, the most challenging part. Okay? Please keep that in mind when you are going through the problems and when you are practicing the problems at the end of the video. Again, I mentioned this in the last video, avoid the temptation to just immediately kind of throw the pen down and say, you know, I can't find the equations, I'm going to look at the answers, I'm going to get the equations, and then I'll finish the problem. If you do that, you have missed the point of this entirely. The point is for you to design the equation to be maximized or minimized. That's really what I'm going to be looking for. So if you again need the solutions to be able to get the equations and then do the problem, it's not going to go very well. Okay? You need to learn how to design the equations yourself without the solutions. Alright, let's begin with the steps. The very first thing you want to do is you're going to be looking for the quantity to be maximized or minimized. Okay. So there's going to be some kind of a quantity in the equation that you are in the question that you're looking for that is meant to be maximized or minimized. Now that could be cost, that could be maximum profit, that could be minimize materials, maximize the area. It can be a lot of different things. So it's our job to figure that out first. What exactly is it that they want me to find? Okay, what do I need to maximize or minimize? That's the first thing we do. Once we figure that out, then we have gotten a good start to our first equation. So, very first thing, determine the quantity to be maximized or minimized. Okay. This is what creates your, I'm going to call it primary, your primary equation. Okay. It's the one that you will be taking the derivative of. So there's going to be, again, a quantity that you will maximize or you will minimize. That will be your primary equation, and that will be the one that you will be taking the derivative of. Okay, the one that has to be maximized or minimized. The one for the quantity to maximize or minimize. That's the primary. Now, that might be all you need. If you've got your primary equation to be maximized or minimized, it's got one variable in it, you've got what you're using to, they've got the function kind of ready with a single changing variable, that might be all you need. Most of what we're going to be going through is trying to maximize or minimize something under some kind of a restraint, okay, a constraint. So you're going to write the equation for the variable quantity you want to maximize or minimize, and you're going to have it in terms of another variable in the problem. Okay? But to do that, you're likely going to need to find the second equation. Right? And that will be based on a constraint. Okay? So a constraint might sound something like, I want to minimize cost, but I have to maintain, this is more expensive than this. Okay, I want to minimize the material used, but I want to make sure I can fit this much in it. Okay, so there's going to be some kind of a constraint involved, again, in most, but not all, of the formulas, questions. So you'll have to use the second equation, the constraint, to help you design the primary equation so that it's in terms of one single variable. Okay, because often there's more than one variable here, and the only way that we can reduce it down to one variable is by using the second equation, the constraint. It makes more sense when we do it, trust me. So once you've got your quantity to be maximized or minimized, in terms of a single variable, you take the derivative, set it to 0, solve. Okay. We're also going to check to make sure that what we found is actually a max or min, because what can happen with some functions is you can have something that looks like this. We want to ensure that if we're trying to maximize, we're getting this solution, not this solution. Okay. Now, many of them will only have one solution, not all though. You're going to find in some of these examples that factoring might, or using the quadratic equation, might be likely. You can tell just by the fact that it's kind of this parabolic shape. There's a good chance that there may be more than one location where you're having that derivative equal 0. So if that's the case, we're going to need to end up factoring or using quadratic. So I don't think I have an example in the video of one that uses the quadratic or factoring. There might be some in the practice. If not, I'm pretty confident I put one in. There will be one in your assignment. So make sure you still remember how to factor and get your roots. Okay. All right. So let's give it a try. So we'll start off with a simpler one just to give you the idea, but then we're going to move into ones that have multiple equations that need to be designed. Okay. All right. Company projects that its total savings in dollars by converting to a solar heating system with a solar collector area in square meters will be the following. Where S is your savings, A is the size of the solar collector in area. We are going to try to find the area that should give the maximum savings. We are also going to try to find the amount of savings that would result in. All right. So my goal here is to find where maximum savings would occur. Okay. So one of the things that we have learned from our previous video is that maximums occur, and minimums for that fact, maximum minimums occur when your slope, for the most part, when your slope is 0. There is a couple of instances, functions that kind of look like, let's see if I can draw this properly, functions that kind of take this awkward shape, where you get the slope is 0, somewhere right around here in the middle. That does not have a maximum or minimum, but for the most part, functions that have your max and min is where your slope is 0. Okay, so since that is when maximum mins occur, it makes sense that if we say, well, max and mins occur when our slope is 0, I know that slope is my derivative, so if I have my function, all I'm really looking for here is my derivative at 0. So that's really the main goal, the main idea behind optimization is you're trying to determine where the derivative is 0. Okay, so you find the derivative, set it to 0, and solve. Okay. The procedure itself is always the same in that way. The only thing, like I said, that makes this challenging for most students is that initial setup. You don't have trouble in general with the derivative, you have the trouble with the setup. Okay. So, but just to remind you that is the goal here. Max and mins occur where derivative is 0, so find derivative, set to 0, find your max or min. And I'll show you how you could verify that you found either the max or the min using a derivative test. Alright, so according to the instructions, I have to determine the quantity to be maximized or minimized. I'm looking to maximize savings. So determine the quantity to be maximized, savings. Write an equation for that quantity in terms of another variable. Well, I don't have to work very hard for it because I actually already have it. I have the formula for savings in terms of area. Okay. Is it a problem that it's an area? Actually, no. Find the area that gives the maximum. So they actually want me to find the area that yields that maximum savings. So it's good that my formula is an area because that's exactly what I want. So there's no reason to play around with this. I don't have to sub anything into it. There's no constraint here. I have what I need. I just need to maximize, find the maximum or minimum of this particular function. So I don't need to write it in terms of another variable because it's already in terms of the variable I am after. Okay. Third step says find the derivative. So let's go ahead. The derivative is 360 minus 0.3 a squared. Alright, that's not too bad of a derivative to take. So just a quick double check. Yeah, looks good. Step 4. Set the derivative equal to 0. Alright. And solve. So I'm going to solve for a. Alright, don't need to worry about plus minus here since it's an area. It should always be positive. So according to this, the savings will be at a maximum when the area is 34.64 square meters. So that is the area that yields the maximum. Area that gives max savings. Because remember, this is what derivatives set to 0 can find. When you say, I want the derivative at 0, equal to 0, what you're saying is, where is the slope 0? And slopes of 0 occur at max and mins. And at the odd time, not a max and min. Okay, but that's part of where this next part, the checking, comes in, is that we do want to check to make sure that we are getting a max and min and not that second scenario that's neither. But before I do that, I do have one more thing to do. It asked me to find the area that gives the maximum. I did that, 34.64 meters squared. It also wants me to find the amount I actually saved. So how do I figure out how much I actually saved? The derivative just gives me the rate of change with respect to area, how the savings is changed as I change the area. To actually get the amount of savings, the total savings, I have to be looking at the original formula. So, if I want to figure out the total savings at the area where savings is a maximum, I'm going to sub in the area that gives the maximum back into the function that gives the savings. And that should tell me how much I saved. There we go. So I subbed the area back into the original, again, not the derivative function, because that'll just yield 0 again. I want to go back to the original, because that's the one that actually represents the monetary, the amount, the savings. And when I sub all that in, I get $8,313.84. Is this in dollars? Yes, dollars. So that is how much I have actually saved. Savings when area is 34.64 square meters. Alright, so I hope this was a good start, and at least an introductory, just to give you a bit of a taste of what we're trying to accomplish. The goal is to find what you are trying to maximize, have a formula for what you're trying to maximize in terms of another variable, okay, one that makes sense for the question, and only one variable. We don't want two in general. Take the derivative of that function once it's been set up. Okay, for the rest of the problems we're going to do in this video, you're going to find this is actually the hardest part because we are going to come up with the formula ourselves. We'll take the derivative, we'll set it to 0, we'll solve, and we'll find out if we have what we have as a value for the max or the min. So before we do that, I do want to mention one more thing. So to finish off this problem, we're actually going to double check to make sure that what we did get was in fact a maximum savings and not, maybe a minimum or that extra scenario where it's neither. To do that, you have to use what are called a derivative test. These are how you can check to make sure that you in fact have a max and min. Another option, a quick option, could be just to check a graph if you have that ability, but not everything can be graphed. So, especially if it's something more three-dimensional, perhaps. A derivative test, though, can be a quick way to check for a max and a min. So to explain to you what these tests do, there are two tests on the page. First derivative test and the second derivative test. I like to try to use the second derivative test more. It is faster, but it's only faster if finding the second derivative is easy to find. Generally, I find it's usually pretty quick with most of these problems because they're usually kind of volumes or areas or perimeters, so they don't have a very high order. So in general, I do like to use the second derivative test. In general, I find it faster. I'll show you what it is. It's at the bottom there. But if the derivative is going to be too hard for me to find, I'll just do the first derivative test. It might take an extra minute or two, but it might be less of a pain in the butt than trying to find a hard derivative. So either one is realistically fine. But again, in my experience, the second derivative test can be faster, as long as the derivative itself, the first derivative you took, what you're left with isn't too difficult to find the next derivative of. Alright, so here's what the first derivative test is all about. I've got 4 images here. 1, 2, 3, 4. First thing to notice is that 3 and 4 don't actually have a max or min. This has a minimum, this has a maximum. Okay. But 3 and 4 don't. Right? Now, they do all have slope equals 0 at C. So here's why we needed this test. If you were to solve for these 4 functions, if you were to get their derivatives, set them to 0, and solve, in each of these examples, you would get C as your answer. In the first example, your derivative is 0 at the minimum, so you get the minimum. The second example, it's 0 at the maximum. 3 and 4, which don't happen too often, but they do occur, is you're getting a derivative 0 here, which is not the max or the min. You can see it kind of looks like it's going to start to be a max, and then it looks like it's going to be a min, so it curves this way. And same with here. Initially it looks like it's going to be a min, then it changes to what looks to be a max, and it ends up being neither. So how do we know which scenario we're getting when we solve for the answer? Because all of these would be answers to the same, steps. Find derivative, set to 0, get my value for C. And again, all of these would be answers to when the slope is 0, the derivative is 0. But we're trying to make sure that we get the right number, the right values, either maximums or minimums when we want them. So here's how this first derivative test works. So here's the textbook definition. If when you look at your derivative, if it changes from positive when you're on the left of C, so think of it as the left of your answer, then it's negative on the right of C, or the right of your answer, you have a maximum. If the derivative goes from a negative value on the left of C, so the left of your answer, to a positive on the right of C, or again, right of your answer, then you will have a minimum. So, as usual, the textbook definitions are not as helpful, I feel like, as they should be. So maybe this will help a little bit more. So this one here, if f prime, so remember that just means slope. If the slope changes from negative to positive, you have a minimum. So look at this first example here. All the slopes on the left of C, the left of where you're finding your minimum, all the slopes from the left side, they would all be negative. Once you're past your minimum point, all the slopes are positive. So if you find the slope on the left side of your answer, and it's negative, and on the right side of your answer, it's positive, it means you have a smiley face, minimum. The opposite is true as well. If f prime, if your derivative, which means your slope, if your slope changes from positive to negative, you have a maximum. So in the upside down frown parabola, the one where we have a maximum, the slope is going to be positive all on the left side of your answer. And as soon as you go to the right side, you start getting negative slopes. So when you go from positive to negative, you get a maximum. That's how the test works. It's meant to show you that depending on what your values are for your slope before and after where you're finding it's 0, you'll be able to tell if it's a max or a min. So before C, again you can think of C as your answer where you're finding slope is 0. So before C, slope going down gives a negative. Slope going up, positive. This would indicate the smiley face, minimum. So let's add that in. So before C, before your answer, slope going down, which means negative answer. Then after C, slope going up, positive answer, you get a minimum. And the opposite. Before C, slope going up, which is a positive answer. Then after C, slope going down is a negative answer. If that happens, that indicates the frown. Maximum. So I'll show you how this works with our first example we just did, so you can see exactly how you actually put this into practice. right now it's just kind of a bunch of words. So let's show you how it actually works when we get back to our example. But before we do that, I will just mention the second derivative test as well. I will do both tests for the first example that we just did so you can see how they work. Second derivative test. So the reason I like this one is if you have your answer, which is pretty much what this means here, if you've taken the derivative, figured out for what value it's 0. If you do the derivative a second time, so you can see there's 2 here, okay, prime, prime. So if you do the second derivative of that function, so the derivative of your derivative, and you sub in the value that you got, that you were looking for, if you get something positive, you have a minimum. If you get something negative, you have a maximum. Okay? So even though this is often easier than the first derivative test, do be aware this can fail due to this issue here. It doesn't pick up on this issue, whereas the first derivative test would. So that can be a bit of a pain. It's not something we have to worry about in our examples, but it's just something I thought I would mention. So how this one would work, let's say this is my current derivative. So right now I've done the question, I've found the derivative, here it is. How do I know, what I'm looking at? So first I'm going to figure out where this function is at a maximum or minimum. I'm going to set it to 0, I'm going to solve, and oops, I like to see that. So I have my function, I've done the derivative of my function, I get 3x minus 9. Okay, I know this is the slope, my slope of my curve. Say, okay, where is this a max or min? Well, that max or min occurs when I take the derivative and set it to 0, where the slope is 0. So then I say, okay, I'll solve for it, so I set 0, I move things around, 9 goes over, 3x equals 9, divide the 3, I get 3. The question is, what did I actually find? Max or min? Well, the second derivative test says, take the derivative once more of the function. Okay? When I take the derivative of 3x minus 9, I get 3. Since f prime prime x is greater than 0, positive, right? That derivative is positive. I don't even have to sub anything in. It's always going to be positive. It's a constant. So because this is positive, whenever it is positive, I have a minimum. So if your derivative isn't too bad, if it's not too hard to take your second derivative, this is a faster method than the first one. I know you haven't seen the first one exactly yet, but this would be faster than trying the first derivative test. The first derivative test is essentially a table of values. Okay? So this can be a little bit faster. That's the idea behind it, is that you can take the second derivative, so essentially finding the slope of the slope to determine whether you've got a max or a min. Okay. All right, so let's go back to that first example. So how would I check to make sure this is a maximum savings like I want? Now, again, realistically, you only do one of these tests. You don't do both. I'm just going to show you both so you can see how they would both be done. Because in our next examples, I'm just going to do whichever one happens to be easiest. So here I can do both, though. First derivative test. So remember what the first derivative test says. It says, from your answer, and my answer was 34.64. So from your answer, you know the slope at this point is 0. I want you to tell me what the slope would be if you had an answer slightly smaller, and slightly bigger than where you are now. Pick something easy, don't make it hard. I'm going to pick 30 and 40. Okay, I just need something slightly lower, slightly higher, and I just pick something even, something easy to use, and I just compute what the derivative would be. So I'm going to sub 30 into this formula here. So I'm looking to see what would be the slope somewhere other than my answer. Because here the slope is 0. I'm curious what's happening before that and after that, so I can see, is it going down and then up, or up and then down? I want to know what's happening. So since I know at my point it's 0, what's happening just before my point? So I sub in 30, 360 minus 0.3, 30 squared, and I get 90. I get positive. What happens when I sub in 40? I get minus 120. Negative. Well, what kind of curve has a positive slope, then 0 as its slope, and then negative slope? Well, that would be the frown. So therefore, it's a max. So it is a maximum, which is what I wanted. Okay, because I can tell before it's 0, the slope is increasing. After 0, it's decreasing. That's what this tells me. I have a positive slope, an increasing slope, then a 0 slope, then a negative slope. And that's what I'm checking for here. Is it changing from positive to negative or negative to positive? The other thing that can happen is if you have positive and positive or negative and negative, that's that third and fourth scenario where you don't have either a max or min. So that's a problem there. That's a problem. We're not going to encounter that. We're going to always be able to find our max and mins, but again, it's something just to be aware of. So if it's positive to negative, it went up and then down, which means I must have had a maximum. Second derivative test. So if your derivative isn't too bad to begin with, so right now I have this as my derivative function. So looking at this, this is just a polynomial. It's not going to be very hard for me to take another derivative. You know, if I had to use the quotient rule or, you know, with a chain rule and it's going to take, be a little bit time consuming, I might just use this one. Okay? But if it's not too bad like this, I would just do the second derivative test instead of this one. So here, second derivative, that's 0 minus 0.6a. Right. So what is my second derivative at my answer? .6, 3464, negative 20.784. Okay. So since the second derivative is less than 0, it's negative, it's a max. Right? So that's how both of the tests are done. Again, you can use either one to check your answers, just to at least verify that you have the max or min. Again, some functions do have multiple answers, and we want to make sure we're using the correct one, so we're not also getting, reporting the maximum when it's actually the minimum. So use those tests at the end of each question to check your answers. Whichever one you want, it does not matter to me. If you'd rather just always be using the first, or you'd rather try to use the second one when it's easiest, that's fine. It really doesn't matter to me. Again, unless I specify on your assignment, you must use the first or second derivative test for a specific question. Use whichever one you want. Whichever one works for you. All right. So, hard to believe, but we are just getting started here. So let's move on to question 2. Remember what the goal is. So this question, the first one we did here, was just to give you an idea of what everything means. The idea behind, once you've got the formula, find the derivative, set it to 0, solve. Check your answer with a derivative test. That's the process that will be involved for all the questions, and it's always the same. what we're going to really be practicing now in these next 3 examples is how you make the formulas that are to be maximized or minimized. So that's what I'm going to focus most of my explanation on. I'll likely just do the derivatives and the solving more quickly, but I want to focus on making sure we understand how to get the formulas. All right, on to the next. Okay, find the dimensions of a 700 kiloliter cylindrical oil storage tank that can be made with the least cost of sheet metal, assuming there is no wasted sheet metal. Okay, so we're going to assume that we're able to use it exactly, get everything to fit exactly, and that's the cost. Okay. All right, so very first step, identify the quantity that you want to maximize or minimize. All right. So I'm really trying to minimize cost of sheet metal. Okay, that's what I'm trying to minimize. Now, if you just kind of stop at, I want to minimize cost, and then you start going with that and saying, okay, well, now I have to find a formula for cost, you're going to find you're going to get stuck pretty quickly, because there is nothing in here that's really going to help you very much with cost itself, right? There's no dollar amounts, there's no nothing like that. So if you kind of get fixated too much on the word cost, you may find yourself getting a little bit stuck. So it's okay if that's how you start, but you want to just keep thinking, if that's not there, maybe what else should I be looking for? So it talks about finding the dimensions of the cylindrical storage tank. So the goal here will be to find the actual things like the height and the radius of the tank that I need to use to minimize cost of sheet metal. And those two things might not feel like they really line up together. You want me to minimize cost, but you're talking about dimensions. Well, how would cost and the size of the tank, the cost of the sheet metal, minimizing cost of sheet metal, and dimensions of the tank, how would those two things really relate to each other? And when we start to think of it more from a production side of things, we realize that what this indicates is I need to minimize the surface area, because that's what determines how much material I use. And if the cost is obviously going to be based on how much material I use, the goal will be to actually minimize materials, and materials is going to be on the surface area of the storage tank. So once I go a little bit deeper into this, I realize that saying, minimize cost, then going, well, you didn't give me anything that has to do anything with costs, dollar figures, how much the sheet metal costs, what am I supposed to do? You realize when you look deeper into this that when it says you need to find, height and radius that is meant to minimize cost of sheet metal, we say, okay, well, cost of sheet metal is going to be making sure that I don't use more than I need to. Okay, I'm going to need to spend the money I need to on the sheet metal, but let's make sure I use as little as possible. And to minimize the material used on the outside, that is my surface area. Okay, so it takes a minute or two to get here, and that's okay. Sometimes, like I said, you get a little, unsure of yourselves and start doubting yourselves a little too quickly if you don't see the answer right away. You're not supposed to see the answer, within the first 3 seconds of reading a problem. You're supposed to problem solve. You're supposed to talk it out, draw a picture, think about what a storage tank would look like if it was being built on a production line. Think deeper into how things are built or how they're used. Okay, so really don't, get down on yourself if it doesn't come to you right away. It's not necessarily going to, and it's not supposed to. You're supposed to take some time to think. Okay? It will come eventually. So I now know what it is I need to actually minimize. So the primary equation to be minimized here is the surface area of a cylinder. Alright, so this is the one where I was getting confused when we did the rate of change examples. We did the other one, the volume of a cylinder, and I was getting confused with the surface area. So the surface area of a cylinder, and you just Google the formula, 2 pi RH. Okay, so this is the side. Again, it's like ripping the label off the soup can. So this is the circumference of the can times the height. So if you rip the soup can label off, you actually get a rectangle. This is length times width, essentially. So then you have your 2 pi r squared, and that represents your top and bottom. So this is the side, this is the top and bottom. It's where how the formula is built. Let's see if I can draw you a little cylinder, but I'm horrible at drawing. There we go. So this is the quantity that I want to minimize. So I've got the equation I want to take the derivative of. I want to set it to 0, and that seems all fine. But you can't quickly jump to the derivative. Unlike the equation before, I've got 2 dimensions in here, radius and height, and both are changing. There's nothing fixed about it. It doesn't say anywhere in the question that the radius must be a certain amount or the height has to be maintained a certain value. We have the ability to change both the radius and the height in order to minimize our costs. So both of these are potentially changing values in order to make sure that we minimize cost. So you might say, well, okay, so if I'm trying to minimize the size, why not just make the radius and height as small as possible? But here's the thing. So here's what we didn't have before. Your job is to minimize the cost with a constraint. Why can't I just make the radius and height as small as I possibly can? Because you are constrained. You have to get dimensions for a 700 kiloliter cylindrical or oil storage tank, which means you must be able to fit that much in the tank. So you are allowed to make it, radius bigger, height smaller, and vice versa. You're allowed to change the 2 dimensions, but you must maintain, and that's 700 kiloliters, remember what kiloliters is a volume. So you must maintain a volume, pi r squared h, equal to 700 kiloliters. So this is your constraint. This is your restriction. It can't just be as simple as saying, well, if I have to make them a minimum, I'll just make them 0 or make them 1. You are constrained to a certain restriction. So there is a primary equation to be minimized. I'm minimizing surface area. This is the one that the derivative will be taken. But before you can do that, you have to input, you have to put in the constraint. Alright, well, how do I put in the constraint? Well, the constraint is there to also help you put this function in terms of one variable. So, since you know pi r squared h must equal 700, that also tells you the relationship that must be maintained between h and r. I now know that h is always going to be 700 divided by pi r squared. That's how those 2 things are going to relate. So even though neither of them are constant, I do know how one relates to the other, which means I can rewrite this formula with one variable, r, instead of r and h. Now I could write it, I could solve this for r. So you might, wonder, well, why do you solve for h? Why not solve for r? Well, look at it. If I try to solve this for r, I'm going to get 700 over h over pi, and then I'm also going to have a square root that I have to then sub back in for r here, r squared here. That's so much more work. Choose the path of least resistance. Find the easiest ways to do these, not the harder ways. Okay? It doesn't matter which variable you use, you just have to have it in terms of one variable. Okay? And that constraint is what will allow you to do that, because it is going to give you the relationship between the multiple changing variables. Okay? Because like we talked about before with our first examples, we can't have multiple changing variables for what we're trying to do. Okay? Again, there's possible, that's related rates, but for here, we want to have the functions in terms of one changing quantity. So, since we have our constraint, we know how the h and the r relate. So I'm going to take this and sub into surface area formula. Two pi r, h I now know is 700 over pi r squared. This had 2 pi r squared, no h in it. I notice the pi's cancel, I notice one of the r's cancel. So 2 times 700, there is 1 r left over on the bottom, plus 2 pi r squared. Right. I am going to do one more step since I do know I'm going to be taking the derivative in a moment. I'm going to get it ready, so I'm going to bring that r up. Alright, there we go. So I have accomplished the second part of what was necessary. So I have found the step number 2. Write an equation for what you're trying to maximize or minimize in terms of another variable of the problem. So I did that. I figured out how to turn this equation for surface area into a formula with one variable, with another variable from the problem, the radius. Because it did ask me to find the dimensions. So there's going to be multiple things I have to find here, the radius and the height. So I'm looking for 2 numbers for my answer. But once I have one answer, I can easily find the other. So I write the formula in terms of one variable, and then I'll worry about the second one when I'm done. Alright. Take derivative, set to 0. Okay. SA prime, negative 1 comes down, 1400, r negative 2, 4 pi r. Alright. So I took the derivative, power rule, brought everything down, dealt with that one. I'm going to set this to 0. I'm going to end up with negative 1400 over r squared plus 4 pi r. And now I have to solve it. So, algebra, 1400 r squared, 4 pi r. So if I bring the r squared up, 4 pi back, I end up with 1400 over 4 pi r cubed. So the cube root of this will give me my r. So I'll do 1400 over 4 pi. .41, so 111.41. To be a little bit more accurate, I'm going to just leave that in the calculator and cube root it, so I'm getting as exact as possible. And I get 4.812. And units, did I have units to go along with this? Doesn't appear I did. So no units to go along with this. So just r is 4.812. Okay, I don't see any units. So 4.812. Alright, so this is the radius that would maximize, would minimize the surface area. Okay, so that is one dimension. Now it asked me to find the dimensions of this cylindrical tank. So I know that the R is 4.812. I also want to know the height. Well, because in most, if not all cases, you've had to isolate for that other variable somewhere before you subbed it in, make sure you go back to that formula. Don't go all the way back to this one where you have to, sub in R and rearrange it. The work should, again, in most, if not all cases, been done already for you. So go back to here and sub that R into that equation. Okay, so you don't have to do any more extra algebra than you need to. So I'm going to sub in the R in for H. And I've lost my calculator. Here we go. 700 divided by pi times 4.8112 squared. Oh, I almost did that wrong. Let's try that one more time. 4.812 squared. Okay. 9.623. 9.623. So my dimensions are right there. So those are the height and radius of the cylindrical tank that will yield the least cost of sheet metal. Okay? Assuming that there's no reason to think that the top or bottom costs more or less than the rest of it. If it's a uniform cost throughout the entire shape, then these are the dimensions I would use. Alright, so there's one more thing we should check. We want to see that we in fact did get a minimum. So just off to the side somewhere we can do a quick check. So the first derivative that was taken, here's the derivative I got when I did it the first time. I could do this a second time, but it's kind of, it's not a super easy derivative to deal with. I guess it wouldn't take that much effort. Yeah, I guess we could do it. It won't take long. So we'll do a second derivative test. Again, feel free to try the first one if you would rather, first derivative test. So you have to figure out a value of R less than 4.8 and one higher, sub it back into the derivative, and see what you get, positive or negative, on the left and right side. I'm going to just do the second derivative. So here was the first one. If I do this a second time, I get 2800 R negative 3 plus 4 pi. So if I sub in my answer for R, let's see what I get. Well, I already know what I'm going to get. I'm going to get a positive. Right? I don't even really need to evaluate it. I know what I'm going to get. I can see just from looking at it, I'm getting a positive number no matter what. So since the second derivative is a positive indicates a minimum. According to the test. And just go back and reference the piece of paper. You obviously don't have to memorize it. Just look at the piece of paper. If it says second derivative greater or less than 0 and what it means. So with a quick peek back at the sheet, I see that the second derivative positive is going to yield a minimum. So I don't even need to finish the calculation. I can tell. This is positive, this is always going to be positive, and certainly this is going to be positive. So, that's all I needed. I don't need the number. I just need to know if it's positive or negative. So if I can make that decision without calculating anything, then great. So we're okay. We've got a minimum. We've got the dimensions. We did it. So you can see it's certainly a longer type of question. It's not, these are not short by any means, and certainly mistakes early on will be difficult to go back and find. So the main thing with these, finding the derivative you know how to do. You've found derivatives now all last week. Subbing something in, solving. You should know how to do that. You know how to set something to 0, how to solve an equation, how to factor. Those are all skills that you have already. The main thing, again, I really want you to focus on and not give up on is designing those equations. All right? Don't give up on those. Those are really what you need to know. Those are what are the new knowledge here in particular. So don't give up on those. Remember, it's find the equation to be minimized or maximized. If there's a constraint, use it to get your variable, one of your variables subbed out for another. Then you can take the derivative. Okay. All right, good job. I know it's a long one. You did good. All right, so we're about to start our third example. We've got 2 more to go. Before I do the next one, though, I thought, again, if you want to have a quick pause in the video, this wouldn't be a bad one to maybe consider trying on your own. Again, remember, don't get flustered right at the beginning. Really try to push through and see if you can figure out how to get those equations, even if you want to stop there and come back to the video and watch the whole calculation part so you don't have to do that part. That would be fine, but I really want you to try. I think it would be a really good idea. This one's not as a good introductory one to try by yourself. Pause the video, see if you can figure out what quantity I want you to maximize and what the constraint is that we're putting on this, and how the new formula, just before you take the derivative, what that new formula is going to be once you have one variable in it. Okay, so once you've used that constraint to figure out how the 2 variables relate, or 3 variables relate, then you can sub them in to minimize or maximize. Okay, so if you want to have a quick pause here, I think it's a good idea. Go ahead and pause. Otherwise, keep listening. All right, so example number 3. The sum of the length L and width W of a rectangular surface is to be 240 centimeters. Determine L and W if the area of the surface is to be a maximum. All right. So I want to determine my dimensions, length and width. If the area of the surface, okay, what surface? Oh, well, the rectangular surface, so I know the shape now as well. So if the area of the rectangular surface is to be at a maximum. So my goal here is to maximize area of rectangle. Well, he didn't give me the area of the rectangle. Well, that's fine. I know what the area of a rectangle is. It's length times width. Okay, so that seems, again, simple enough. You want me to maximize the formula for the area of a rectangle. Okay, but the problem is I have length and width. So what exactly is it I take the derivative of? The L or the W? Well, that's the thing. You can't really do either. Both of them are changing quantities. If you are trying to maximize the area of the surface, you might be changing the length and the width. They can both move and change to change the area of a rectangular surface. So there's not a lot you can do right now because you have 2 changing variables. You have a formula in terms of 2 variables that are changing, so that's not going to work right now. Let's see what kind of restraint we have. Okay. It is also possible to have more than one constraint. Okay. You may find that there is more than one constraint that you are meant to use to help you eliminate, I shouldn't say eliminate, but in order to reduce the formula down to one variable, okay, to take the derivative of. So be aware you can sometimes have more than one constraint. So the constraint here, what do I need? Well, what else do I know about this rectangular surface? The sum of the length and the width has to be 240 centimeters. So I have to make sure that when I've created the area, the maximum area that I can, I have to maintain a length plus a width equal to 240 centimeters. That's my constraint. So that tells me how the length and width have to act with each other. They have to make sure that once you figure out the maximum of one, this one still has to be, you know, we can't just say, well, let's just make them both as big as possible, because the two of them must combine to make 240. So this is how we're constrained. So using that, we can get this formula down to one variable. So if I isolate for L, let's say, again, it doesn't matter, you can choose W or L, makes no difference. So if I decide that L is 240 minus W, okay, using that, I can sub that in so that I have a formula for area that just has W. So I have the formula that needs to be maximized in terms of another variable from the problem that I need, the width, okay, which is what I want to be doing. Okay, I don't want to be taking the derivative of two changing quantities. Again, that involves higher order calculus that we just don't have the time to go through. So there's my formula to be maximized. So let's find maximum. Find derivative and set to 0. So here's the initial formula before I've taken the derivative. Okay, make sure you don't go so quick you forget to take the derivative. I've seen that before. So the derivative here is 240 minus 2w. Set this equal to 0. Solve. So bring this over. 2w equals 240. So w equals 120. So this is the width we would want the rectangular surface to have in order for it to be a maximum. Now it though asks me to find the length and width. Well, that's okay, since I know the width that now must have to have the maximum. I can find the length because I have the formula up here. So the length that's going to yield a maximum must be 120. And if you notice a little further, length and width are equal. So maximum area would be a square. Okay, this is pretty. This is a. What do I want to call it? I don't want to say a property per se, but this is what happens when you try to maximize rectangles. The maximum of rectangles are squares. Okay, so the dimensions are always equal for maximizing rectangles because you get squares. Just as a little, though, I guess a footnote to that is that's assuming that there's no difference between, you know, the length and the width. You know, if you're doing something like cost and you're saying, you know, the cost, the length is twice the width or something like that, that changes things, of course. But assuming you're just trying to maximize the area of a rectangle, then yeah, you're always going to find it's a square. Alright, so there's that one. That one was much shorter than the first one. Again, the main thing I really want you to see and about what I'm doing here is how I'm getting those initial equations, because that's really what I'm going to be looking for. You know, when we look at what you learned from this unit, I want you to be able to find these formulas. Okay, find the ones that you're going to maximize, use the constraints to get you to this point. Okay, you know, everything that happens after, you know, is very mathematical. It's the same steps. You know, find derivative, set to 0, check your answer. So that's all pretty step by step. Okay, but that initial finding of equations is what I really want you to try to work on. Okay, so like I said, as tempted as you are, when you do these problems, do not give up on the equations. That's what you're really trying to learn. If you keep looking at the answers to get the equations just so you can find the derivative, you're missing the point. Okay. Alright, I'm going to do one more thing here. I am going to quickly do my second derivative test. And just verify that I do in fact have a maximum. So here's my first derivative, a prime, 240 minus 2w. So my second derivative test, I get, well, that's constant, so that's 0. I get -2. So I don't even have to go about subbing in w because there is no w. I know, I can see that the second one is negative, and if the second derivative is negative, then I know I have a maximum. So quick check, yes, I do have the maximum. All right, we're getting there. We got one more example to go through. Right? It feels weird doing this in videos because normally I would get to pause and let you guys practice and talk to you and get you to ask questions, but in a video it's just me talking over and over again. So it feels a little strange. All right, number 4, last one, I believe. All right, you can have a quick read if you want before we get started. All right, just looking through my notes here to actually find what I need for this problem. There it is. All right, so last one. But I did save the hardest for last, so. An engineer is designing a rectangular frame with 4 sides, in which the front side costs twice as much per centimeter as the other 3 sides. The frame must have an area inside of it of 1,350 square centimeters. What dimensions must it have such that the cost of the sides is at a minimum? Okay. So I am going to help you get a little started with this one because this would be hard to just kind of jump in with. So for whatever reason, the front side is costing twice as much per centimeter as the other 3 sides. Now you might notice it actually doesn't say what that cost is, it just says it's twice as much. That's okay. Even without a numerical value for cost, we can still do this. So what do we know? We know that inside the frame, we want to be able to fit this much. We know that the cost is twice as much. We don't know what that cost is, so let's just call it X, but it's twice as much per centimeter on the front, okay, as it is the other 3 sides. Okay. So you might also kind of think, you know, how do you know that's the front? What if it's the long side? It won't matter. Okay, the answer will work out no matter you know, where I put that 2x, if it's a long side or a short side, it's going to work out the way it's supposed to. So it's okay if my diagram maybe isn't reflecting exactly where the 2x is supposed to be. If it's supposed to be on a long side or a short side, it won't matter. Okay, I just need to get an idea of the concept. Okay. All right, so we've got our cost, our area inside. The cost is just being measured kind of on a linear basis, one dimension, so it's just, you know, cost is based on the centimeter of the length of the frame. All right. So that's the part I really wanted to help you out with, though, just to get you started, because that can be a little confusing when you read that first line. You're not really sure what to do with that information. So hopefully that makes sense when you reread that first line as well as the second line. So just one more time. You have a rectangular frame, 4 sides. The front costs twice as much as the other 3 sides. The inside area has to be 1,350. Okay, so front twice as much, so I called it 2x. Doesn't matter what the cost is, $4 per centimeter, $6 per centimeter, 3 cents per centimeter. I know it's going to cost twice as much as the other 3. So I can use x, it'll be fine. You'll see that it'll work out even without that information. You know, you can't use what you don't have. So if we don't have the cost exactly, that's fine, but we do know the ratio of costs between sides. All right, what am I trying to do? Now that I have a bit of an idea of the concept, they want me to say, find what dimensions. Well, it's a rectangle, so it must mean length and width. Will this have, so that the cost is at a minimum. So if I want to make this at a minimum cost, how would I do this? So the goal here is to minimize cost. Now, before, when we had the very first example, we talked about cost, and we said, well, we didn't have anything to actually talk about cost, you know, dollars or any kind of sense of money. So we realized that, you know, the cost really came down to minimizing surface area, right? That is similar to what's happening here, but not exactly the same. Here we really are trying to minimize cost. So before we kind of bounced around from saying, well, instead of using cost, we'll minimize surface area, because that's the same idea. Here we are actually going to come up with an equation for cost, because we have an idea of cost in relation to dollar amounts in our sides, in our shape. So here we do want to actually implement the idea of cost. Alright, how do we find cost? Well, if the idea is to minimize it, we have to know what cost means. Well, cost would be dollar amount. It would make sense that the cost to make this, you know, if you think about it as logically and as simple as you can, how would I figure out how much it costs me to make this object? Well, cost should be the dollar amount times amount of material. Okay. In our first example, when we changed from saying, you know, well, minimum cost would just be the same as minimum amount of material, that was true. So here, you know, we could say, you know, cost is equivalent to the amount of material, but because there is different costs for different parts of the shape, we need to take that into account. So we have to add in this idea of, you know, taking the amount times the amount of material in order to get actual cost. So again, just to give you an idea of why this is different than before, again, the reason this is different from before is because one of the sides is costing different than the others. If they all cost X amount, then it wouldn't matter, right? I could use just, you know, minimize the perimeter, and I would have what I want. So it wouldn't matter. You know, I don't have to factor in the fact that, again, I don't know what cost is, won't play into this at all. I just need to minimize the perimeter. But because I've got one side costing a different amount than the other, in fact it costs more, what I'm likely going to be trying to do here is make sure that I keep this one as small as possible, because it costs more, while also making sure I can maintain that area. Okay, so there's a little more going on here, so we have to take into account the amount as well as the amount of material used for that amount, because that's what's going to impact our cost, because there is different amounts. Alright, so in this case I've got 2x times, well, it's a rectangle, so I've got length, width, and width. So I've got 2x times the length, that's what that's going to cost me to make the front side. It's also going to cost me X amount of dollars to make the width, and X amount of dollars to make the length, and X amount of dollars to make the width. So that's what it's going to cost me to make this item. Alright, if we simplify this a little bit, we can remove the dollar signs and collect some terms. I'll get like terms here and like terms here. So I'll get 3xl plus 2wx. So there we are. There is our formula for cost. So again, it can seem a little overwhelming when you first read it, but again, don't be afraid to let this take you some time. This will take you time. It's supposed to take you time. You know, no student can really look at this and just immediately, you know, I know exactly what that formula is going to be. You know, we need to write a diagram. We need to write it out in words. We need to let it play through our heads. So please don't give up on these equations right away just because they don't come to you immediately. Try something, okay? Play around with it. See if it means what you want it to mean. Really think as logically and you know, as much in real life application as you can. It will make that easier for you. Alright, well unfortunately we can't use the formula as it is, can we? We have length and width. Both could potentially change in order for us to minimize cost. They're both changing values. What else do I have? Well, I have a constraint. I have to keep the area of the rectangle inside at 1350, which means I know length is equal to 1350 over W. That's the relationship that has to be maintained here in order to ensure the area will always be 1350. So in order for me to make sure I always have an area equal to 1350, this must be true at all times. Okay? So since that must be true, I can sub that into my equation. So cost there it is. Alright, I'm going to simplify that a little bit. I also know I'm going to be taking a derivative, so I'm going to bring this up. To Wx. Alright. So, I've got my cost. It is in terms of one changing variable instead of two, which is what I needed. I don't have to worry about the fact that I don't have the L in there. I know that L and W are related in this way, and I've taken that into account. The other thing I don't have to worry about is you may be wondering about the x's. You know, why haven't I subbed out the x's, or why am I not worrying about the x's? Well, it's because the x's are, first of all, constant. They are just the cost of the walls. I just don't know what they are. That cost is not a changing quantity, so it doesn't matter that they're in the formula. You're going to see that it's not going to make a difference. You'll see what happens towards the end with those x's. But I'm not concerned about them because they're not changing. They are just the cost of the walls. They have nothing to do with you know, my ability to minimize that perimeter based on that cost ratio, 2x for the front, x for the rest, and they don't impact my area, so I have no concerns with leaving the x's in there, even though I don't know what they are. Alright, let's find the cost derivative. The negative comes down in front, W becomes -2, and I get 2x. So I set that to 0. Alright, I'm also going to bring that W down so it's not on the top anymore. Alright, set to 0. I just brought that down so it's a little easier for me to work with now. And I'm going to go ahead and solve. Alright, so I want you to see, look what happens with those x's. Alright, so they won't make a difference. Well, this is why. Alright, they were going to cancel out anyway. Okay. I didn't need to worry about it because they weren't going to cause any problems. They were going to cancel. Do we have a length? Yep, centimeters. Alright, so we have the width that will minimize cost. Okay. So, therefore, we've got W 45 centimeters, length 1350 over 45. Okay, that's from the formula up top. You can pause and have a quick look up if you need to. Alright, just go up to near the top of the page there. You'll see L equal to this. That's from your constraint. So as soon as I know W, I know L. So I've got my width is 45, my length is 30. So those are the dimensions to minimize cost. Okay. So it looks like, yes, I did have it right in my diagram anyway, which kind of makes sense. If the front's going to cost twice as much, it's probably going to be a smaller side anyway. So this is the length, the front, that'll cost twice as much, as well as the back, and these are the two sides, 45 centimeters. Okay, so those are the dimensions that I need to use to minimize cost. All right. And we should do a quick check as well. So those are the dimensions I need that will minimize cost and keep the area to 1350 square centimeters. Let's do one last thing really quickly. Let's do our first derivative test. Okay. So I know, again, as we're getting to the end here, because we are almost done, as we get to the end here, I know just with videos you can't stop me and ask questions in the middle, but remember, you can always stop a video, maybe make note of the timestamp, and ask me a question, you know, what did I mean by this at this time, or something like that. So again, if you have any questions along the way, it doesn't mean that you can't ask them. You just have to kind of keep track of them a little bit more. Maybe jot them down, maybe jot down what video so I know where to look. But you can certainly still ask questions. Like I said, it feels odd me talking so long about these questions and nobody asking any questions, but you can still ask them, of course. Alright, so remember, if you get confused, ask questions. Alright, last thing, let's check our test. I think I did a lot of second derivative tests, so how about we do a first? So first derivative test, let's do it off to the side here. Alright, so my cost derivative. So when W is 45, that's where I was seeing the cost equal to 0. Alright, the question is, this is what I got as my answer. The cost, the derivative is 0 when W is 45. What happens when W is less than 45? Well, I'm going to pick an easy one. I'm going to pick 0 because that's less than 45. And how about when it's 50, something above? Alright, so what I have to do is I have to sub 0 and 50 back in to this equation here. So I'm going to sub 0 and 50 back into this equation. Alright, and I'm going to solve for it. Okay, so here we go. I'm just realizing 0 is not a good choice because the width obviously can't be 0 because then I would not have a rectangle. So as much as nice and easy choice that would have been, that won't work. So let's just choose something a little easier than just 40. Yeah, you can't have the width be 0 because then you have nothing. So that's not a real answer for a W. That would be division by 0. So let's try that one more time. So subbing this back into the derivative with 40 as W gives me this plus 2x. 450 divided by 40 squared. Alright, so that's what I get for now. I'm going to explain that in just a second. I'm going to do the next one real quick before I give you the rundown on what's happening. So when I do it one more time with the 50 instead, alright, so here's what I'm getting as my derivatives, my slopes. So this is meant to be my check whether I'm getting a minimum or a maximum. So you can see this took longer than second derivative in most cases, which is why I don't do it unless I have to. I could have just done the second derivative test. You know, I think that would have been faster here still. This is kind of a longer way to do it, but it might make more sense to you. So if it does, then great, go with it. So here's all the work done so far. Let's go over it. So I've done this first derivative test. I figured out that this is my answer from the question. This is the slope, 0, right? This slope 0 is what gave this answer. This is where the maximum or minimum is occurring. What I'm looking for here is whether I have the smile or the frown, upside down or right side up. So what I do is I choose arbitrary values, one lower, one higher. Again, I just chose these at random. Okay, I chose 0 at the first point, which was silly because I can't have a width of 0, but I could have chosen anything else. 2, 4, 10. I decided to go with 40 and 50. I just tried to choose something easy enough, so I did those two. What I then have to do is sub 40 and 50 into the formula. If you sub 45 in, you get 0, because that's the point. You're going to get your slope is 0 there. What is your slope when you're at 40? What is your slope when you're at 50? Now remember, it doesn't actually matter the number, because when you look at this and you say, okay, well, pardon me, I subbed in 40. I didn't get an answer. I got the thing with X. You know, that doesn't tell me anything. Or you say, well, I subbed in 50, and I got a number with an X. That, again, didn't tell me a number. How am I supposed to know? Well, as soon as you remember, well, what is X? X was the cost of the wall. Well, the cost, of course, has to be positive. It couldn't be negative. So you get a negative times a positive. And a negative times a positive is always going to yield a negative. So even though I'm not getting a numerical answer, I can still know for sure that this is a negative slope, because cost, X, which is from our problem, is got to be positive. Same here. I have positive 0.38 times a positive cost. That definitely yields a positive. What type of answer goes from having a negative slope to a positive one? A minimum. Okay? That's the one that goes down and then up. So you have a minimum. Okay. All right. Well, you did it. Good job.